Hello everyone, this is GATE 2012 question. It's a 2 marks question. Question number 47 I have taken. So it states that at a certain temperature T, the average speed of nitrogen molecules in air is found to be 400 meter per second. Just a minute. So it is 400 meter per second. Now what we need to find out is the most probable and the root mean square speeds of the molecules are respectively, and these are the 4 options which are given. So one of them will be the correct options. So it's a 2 marks question which is based particularly on the concept of kinetic theory of gases, and particularly what are these average speeds, most probable and root mean square speeds. We will see and find out what is the most probable and root mean square speed in case when the average speed of the nitrogen molecules are given to be 400 meter per second. So let's see the step-by-step solution. So this is the question number 47 solution. So what is given in the question is that the average speed of nitrogen molecule at temperature T is found to be 400 meter per second. Now what need to be found out is the most probable speed and the root mean square speed. Now the concept here is that the distribution of this molecular velocity, we have been given in the question about the nitrogen molecule at particular temperature. So the basic concept behind this particular question is that the distribution of the molecular velocity of a perfect gas is given by the Maxwell-Boltzmann distribution. This we need to remember. The Maxwell-Boltzmann distribution, which states that this is the Maxwell-Boltzmann distribution. Remember, this is the probability distribution. Distribution, or you can say that it's a probability density kind of thing. So it's dNV is equal to 4 pi a cube n v square e to the power minus bv square dv. Now what does it represent? We will see with the sketch which I have drawn below, where a is equal to root over b by pi and b is equal to m by 2 kbt. We can find out from by equating this dNV and integrating it from 0 to infinity for all possible velocities. We can find out this particular expression: a is equal to root over b by pi and b is equal to m by 2 kbt. Now b is equal to m by 2 kbt. If we put it here, then we will get the constants a and b, and then we can use those particular expressions. Now what does this particular distribution says? If I write it like this, dNV by dV, just writing the dV in the denominator. So dNV by dV is actually this particular expression, 4 pi a cube n v square e to the power minus bv square, where the constants represent these are the values. So it just says that it's a v square into e to the power 1. One is a square function and there is the exponential decaying function. So this is the kind of a graph which is expected. Now here what we this particular axis is the velocity axis v, and this is dNV dv. This is the probability distribution function or density function. Now this is the distribution. This is the Maxwell-Boltzmann distribution, and all the molecular velocity of the perfect gas follows this kind of distribution. Now what does this area under the graph shows? This area under the graph which I have drawn between v and v plus dv, I have shaded. So the area under the curve, it shows the number of gas molecules just a minute, present in between velocities v and v plus dv. So in between v and v plus dv, or molecules, instead of saying present, we can write it as having. Molecules having velocities in between v and v plus dv. So in between V and V plus dV, this area under the curve shows that this is the number of gas molecules having velocities in between V and V plus dV. Now, this is the average velocity. These are the definitions and the formula of the average velocity, root mean square velocity, and the most probable velocity. From the graph itself, we can find out what is the most probable velocity. As we know that the most probable thing is the maximum of a particular probability density function. So this is what where this slope of this is 0 is actually the most probable velocity. So what is the definition of most probable velocity? Is that ddv of dnv by dv should be equal to 0. Whichever velocity for that it is equal to 0 is the most probable velocity. Or where this function becomes maximum, that velocity at which the function dnv dv becomes maximum is your most probable velocity. So we can also write that velocity where dnv by dv becomes maximum. Okay. And its value comes out to be root over 2 kBT by m. If you just follow this particular expression and just differentiate it using this particular formula, this distribution, then we will get Vp is equal to root over 2 kBT by m. Average velocity V bar is the typical definition of the average, 0 to infinity for all possible velocities V dnv, and again in the denominator it will be divided by 0 to infinity all possible velocities dnv, because remember dnv has, in the dnv expression we have dv also. So that will result into root over 8 kBT by pi m as the expression of the average velocity. Root mean square velocity is defined like this, 0 to infinity v square dnv upon 0 to infinity dnv, and it is vrms square, so it will be square of root over 3 kBT by m. Therefore vrms, from here we can say that vrms is actually root over 3 kBT by m, where kb is the Boltzmann constant. Now in the question it is given that v bar, that is the average velocity, is 400 meter per second. So we equate this equal to the formula of average velocity, that is root 8 kBT by pi m. So we have equated it, and just we found out from here the kBT by m expression, because you can see that in RMS also kBT by m is there and under the root, and in the most probable velocity also kBT by m is there. So it is the common factor. So kBT by m I found out from here. After that I just put in the Vp, the most probable speed, 2 kBT by m, that is root over 2 into that particular expression of kBT by m I just put, and it comes out to be about 354.5 meter per second. Similarly vrms, it is root 3 kBT by m as per the definition. We just put into the value, it comes out to be about 434.1 meter per second. And if you come to the question again, it is the option A which goes more close. There is 354.5 is close to 355 and 434.1 is close to 434 meter per second. Therefore, at a certain temperature T, if the average speed of the nitrogen molecules in the air is given, that is 400 meter per second, the most probable and the root mean square speeds of the molecules are given by 355 and 434 meter per second respectively. So option A is the correct option. Thank you.